morning, ladies and gentlemen. My name is Samira Douzi. I am from University Mohammed V in Morocco. I will present my research about unmasking honey adulteration using thermal images and convolutional neural network. Okay, honey is a naturally sweet material made by honeybees from floral nectar. It has been ingested by humans for thousands of years and is prized not only for its sweetness, but also for its numerous health advantages. It comprises essential vitamins, minerals, antioxidants, and enzymes that provide advantageous effects on human health. However, the purity of honey has become a concern due to the widespread issue of adulteration. Adulteration refers to the addition of substances or the modification of honey to increase volume or alter its appearance, taste, or aroma. Common adulterants include sugar syrup, corn syrup, and other sweeteners. This not only compromises the quality and nutritional value of honey, but also poses health risk to consumer. So, in response to the growing concern of honey adulteration, we propose an approach leveraging thermal imaging and deep learning techniques to detect adulteration. By capturing the thermal images of honey samples using infrared camera, we can exploit the inherent temperature variation associated with pure and adulterated honey. Through the application of computer vision algorithms, specifically CNN models, we can train these models to recognize and classify this thermal pattern. So for this purpose, a set of 24 time honey sample was prepared, which included 10 pure honey samples, as well as honey samples that had been corrupted with 10%, 25%, and 50% sugar syrup. The samples were subjected to the temperature of 60 degrees. We use a thermal camera to capture the thermal radiation raised by honey during the culling process. Each honey sample was recorded in a series of 15-minute clips. The thermal camera is used to visualize the spatial distribution of thermal energy on each sample surface. For these clips, we extract frame which provide us a database with 360 frame. So we extract from each clips we recorded, we extract frame for pure honey and adulterated honey, and we got 360 images like this. So after extraction of the frame, the next step is in our approach is the identification of area of significance in image. For that, we employed the contour detection technique. By this method, we were able to save only the pertinent portion of each thermal image. Here we can see that we have a background, a blue background. So we remove this background and preserve only the portion, the pertinent portion of image. The next step is to improve the diversity of our thermal dataset and the resilience of the convolutional neural network models that we will train on this dataset. For that, we used an augmentation approach called temperature fluctuation. So temperature fluctuation technique consists of adding random perturbation to the original image, to each pixel intensity of thermal image, which creates artificial variation in temperature. To illustrate the level of change in each color, channel between the generate and the original image, we compute the difference, the absolute difference for each channel separately. We can see that here, we can see that we have brighter section. This section represents location where there have been more significant change to the pixel value between the original and the produced image, while colored portion show region where the pixel value have changed by smaller amounts. So we have brighter section and colored section in each channel. So as a result of this step, we obtained an additional 360 image that will significantly expand the diversity of our thermal dataset. So we have in the first we have only 360 image. By augmentation, we have 720 images. After that, we train for convolutional neural network architecture, Xception, ResNet, VG19, Xception, and also we have proposed CNN model that we trained to on the same database. So we train the four this models are the cutting edge of CNN model, and we proposed new models, CNN models, that we will train it. We train it also on the same database. So for the performances, the finding demonstrate that nearly all algorithms possess the capability to classify contaminated honey with different concentration. Furthermore, the performance results illustrate that our CNN model outperforms the other CNN models in detecting honey adulteration. The effectiveness of our suggested model can be explained by the fact that the models, the four models, VGG, Xception, ResNet, Xception, underwent initial training on the ImageNet dataset, which is made up of a diverse range of images with content, features, and patterns that differ significantly from thermal images. So to conclude, this study has investigated the issue of honey adulteration by using thermal image and CNN architecture. We use temperature fluctuation technique to augment thermal dataset and to increase the resilience of the model CNN. We proposed CNN model characterized by its simplicity and that outperformed tainted model as VGG ResNet. We observed that the model have the ability to classify contaminated honey with different concentration, 10%, 25%, and 50%. Our future work include the investigation of novel deep learning models, examining diverse honey variety and adulteration level, and extending this methodology to encompass additional food items. Thank you.